Okay, so let's go ahead and get started. Homework 10 is out. It will not be as evil as homework 9. I'm curious to see how what people did on question 2. Because so far I've heard of 5 different ways to do it, all of which will work. You'll see my official solution once I post it after class. Okay, so this week we're going to finish up talking about NP-hardness. Then there's a break, and then the last week we're going to be spending about actually proving things, not just that things are hard to compute, but they're in fact impossible to compute. But it's a little easier to start out by trying to prove things are hard to compute. So there's this $1 million question, and I mean that literally. The Clay Mathematics Institute back in 2000 posted a list of the 7 most important open questions in mathematics. This was question number 1. If you solve it, they will give you $1 million, but on the other hand, if you solve it, they will give you a Turing Award and then immediately rename the Turing Award after you. So a mere $1 million is probably not the most that would come out of this. It's number 1 for a reason, because if the answer to this is yes, then the other 5 that are still open either don't have a short proof at all and there's no hope of proving it, or there is a short proof and therefore, because P equals NP, we can find it quickly. It's just a matter of writing the code. So if just to remind everybody what this means, intuitively at least, P is the set of problems that can be solved from scratch in polynomial time. And NP, although there are some technical limitations on what I'm about to write, you should think of NP as a set of problems where if you already know the solution, you can, in principle, convince somebody else that it's correct in polynomial time. Meaning, for example, if there's a solution to a homework question, you don't just have the answer yes or no, but you have the intermediate work as well. Yes?
I was going to say, how does solvable and verifiable?
I'm being deliberately informal here. In fact, the proper definition is P means it's a language that can be decided in polynomial time. And NP means it's a language that can be decided in non-deterministic polynomial time. But the latter phrase means there is a polynomial time Turing machine which you can feed a string and something else. And if the string is in the language, then there is a something else that will make the machine accept. And if the string is not in the language, then there is no something else that will make the machine accept. Okay. But for purposes of intuition, it's fine just to say P are things you can do from scratch quickly. NP are the things that once somebody has done it, you can check their work quickly. Okay. Now, there's a related class of problems that are called NP-hard. And what this means is if X is in P, then in fact P and NP are the same. So if there is a fast algorithm for an NP-hard problem, there is a fast algorithm for every problem in NP. Anything that you could check quickly, you could solve quickly from scratch. Okay. Nobody believes that P equals NP. Not many people believe that P equals NP, and therefore the intuitive conclusion from proving that a problem is NP-hard is you can't solve it in polynomial time. And unless you're one of the small group of people who are devoted to actually proving this, chances are if you really want a solution to this problem, you need to move away from the model that we've used in this class of trying to find algorithms that are correct for all inputs or that are efficient for all inputs. Or maybe you don't want the exact optimum answer, but you're okay with something that's within 5%. Or maybe there's some structure in the instances that you actually need to solve the problem on that allows some other methods to work for inputs with that structure, but which wouldn't work in the more general setting. Lots of different ways to attack these things, but here we're just trying to show that you have to use some specialized knowledge or you have to change the problem in order to solve it. Okay. Now, there's this theorem by Cook-Levin, which says this canonical problem called circuit SAT is in fact NP-hard. And I sketched a complicated reduction that says, if you give me one of those non-deterministic polynomial time Turing machines, I can turn it into a circuit. And then the question, is there a proof that would convince the machine that this string is in the language, is the same as, can I set the switches so that at the bottom of the circuit the light turns on? And so if I could figure out whether a given circuit is satisfiable, magically I could solve any NP-hard problem quickly by just building the Turing machine simulating circuit. It's not a nice polynomial, but it's still polynomial. And so as a consequence, what this means for us is that if I want to prove that a problem X is NP-hard, all I have to do is reduce circuit SAT to X. What this means is, if I have a new problem and I don't know whether it's hard or not, and want to prove that it's hard, I'm going to start out thinking in terms of proof by contradiction. I'm going to assume, suppose for the sake of argument, that there is a fast algorithm for X. I don't know what it looks like. I don't actually care what it looks like. I know what the problem's specification is, and I assume magically a box floats down from the clouds with rainbows and unicorns all over it that magically solves the problem X. And when I say reduce circuit SAT to that, what that means is I'm going to build an algorithm that solves circuit SAT in polynomial time by invoking this black box as a subroutine. And so the implication is that there is a fast algorithm for circuit SAT. But that would imply P equals NP, which nobody believes. And so reversing the logic, that means we should not believe that X has a polynomial time algorithm either. Okay, we started off assuming there is a fast algorithm, and we end up deriving what's essentially a contradiction. All right? Now, so I'm going to rewrite this again because it'll prove that X is NP-hard. I want to reduce circuit SAT to X. Now, at the very end of class last time, we used this technique to prove that another problem is NP-hard. So we saw that formula SAT, which is usually just called SAT, is NP-hard. Using the reduction from circuit SAT. So the input to SAT is a formula. It's a collection of, it's a string of symbols. Parentheses and or not implies equals exclusive or and variables. And the question that you want to ask for SAT, is there a way to assign true false values to the variables so that the entire expression is equal to true, right? And it's maybe not surprising that sat and circuit sat are roughly equivalent to each other. I can take any circuit and just write it down carefully as a formula. And similarly, given the formula, I can evaluate that formula in hardware by building a circuit. And that's essentially what the reduction argued, is that let's explain how exactly you would transcribe a circuit as a formula. The magic black box for formula sat just tells you whether the formula is satisfiable. And then but you know, because you built the reduction correctly, the formula is satisfiable if and only if the original circuit is. So I've got a fast algorithm for circuit sat. But the nice thing about this implication is that if I want to prove that a problem is NP-hard, I can either reduce circuit sat to that problem, or I can reduce formula sat to that problem. And this list is going to get longer. Every time you prove that a problem is NP-hard, you can add it to this list of problems you reduce from to prove other things are NP-hard. So I'm going to go through several such problems. There's a variant called 3-sat, which I'll walk through carefully. There's some graph coloring problems. You can find cliques. You can do traveling salesman, for example. There are various scheduling problems. There's all sorts of silly problems with games and puzzles that I won't have time to talk about. But every time somebody proves that a problem is NP-hard, it gets added on to this list of things you can reduce from. So in some philosophical sense, this is very much the same as building up a library of algorithms. Whenever you want to build up a library, you can invoke the code that you've already written for other problems as subroutines as you build the library for new problems, right? Except now, again, the argument is backwards. I know that for everything in this list, there is no polynomial time algorithm. And so if I'm faced with a new problem and I want to show that it also has no polynomial time algorithm, I have my choice of what things on the left to try to implement using a magic black box for X. Okay. This will become clearer as we build up longer examples. Right? So, does anybody have any questions about definitions? I'll go through a couple more examples of reductions. So if you have a question about exactly what a reduction is, hopefully that'll be clarified soon. But other than that, any questions about what we're trying to do? It is very easy. Many, many people do this. It is very easy to get the direction of this reduction backwards, which is why I always recommend thinking about it as a proof by contradiction. I want to show that this problem is hard. Let's assume this is easy and figure out what ridiculous consequences follow. Okay? All right. So let me give you another example. And it's an example that actually tends to be the sort of canonical starting point for almost every other NP-hardness proof. All right. So this is called 3CNF-sat, or usually just 3-sat. Okay. Now, this is a special case of formula satisfiability. And it's a special case because the formula that you're given as input is assumed to have a particular structure. So that structure looks like this. Right, so let's just put dots here. The formula is very flat. Right, there's only one level of parenthesis nesting. And the formula is composed of clauses that are anded together. This is called conjunctive normal form because and is the three-letter word for which the long, highly educated, overpaid Latin word is conjunction. Okay. So a three-sat formula is a conjunction of clauses where each clause is composed of exactly three literals that are themselves ORed together, and every literal is either a variable or the negation of a variable. Okay, so if I wanted to imagine what a 3CNF formula looks like as a circuit, okay, so I have the inputs coming over here, A, B, C, D, E. For each variable, I'm going to split it into two wires, one of which is going to be negated. I'm going to do that for every variable. Then there's this huge tangle of cables, no gates at all. It's just cross-wiring the variables and their negations to the stuff on the right side of the mess. And what goes on the right side of the mess is that I have triples that are ORed together. These represent the clauses. And then all the clauses are glued together in one big AND. Okay? So this is a very, very rigid structure. And what is especially interesting about this is it is not the case that you can describe every Boolean function in this form. You can't, right? There are functions that cannot be described in this form. The easiest being A or B or C or D. Okay. Nevertheless, this special case of 3-sat is still hard. Now, normally, when you're thinking about special cases, you say, oh, I've already got an algorithm for the more general case. I already know that sorting can be done in n log n time, and therefore sorting even numbers can be done in n log n time. Right? Therefore, sorting n integers each between 1 and n can be done in n log n time. Right? That doesn't rule out the possibility of a faster algorithm, but you know at least that there is an algorithm. When you're talking about special cases in this context, remember that when we say there's no fast algorithm, that means there's no fast algorithm that consistently deals with all possible inputs. In principle, it's possible that there may be no algorithm that can solve formula set for arbitrary formulas, but still that doesn't rule out the possibility that formulas with this particular structure, there might be a faster algorithm. And in fact, if I said 2 here instead of 3, if I only allowed clauses to have 2 literals, there is a faster algorithm. There is an algorithm to solve 2-sat in polynomial time that ultimately boils down to depth-first search. Okay. But for 3-sat, this turns out to still be hard. Okay? So I want to try to convince you of this by walking through a reduction. It turns out to actually be somewhat easier to walk through a reduction directly from circuit sat all the way to 3-sat instead of going from what seems like it would be simpler, the more general formula problem. Okay. So everybody understand what the problem is. I'm given this AND of a bunch of clauses, each of which is the OR of a bunch of literals, each of which is a variable or its negation. And I want to know if I can assign true-false values to the variables so that this whole expression evaluates to true. Okay. So here's how we start. So remember, I want to do a reduction from circuit SAT. So the algorithm that I want to write starts with given an arbitrary Boolean circuit K. Okay, and I want to derive an algorithm that will solve the satisfiability problem for K given a magic black box for 3-SAT. Okay, now the reduction is going to go in several stages. The first stage is I want to put K, I want to make sure that K is in a certain canonical form, which is all AND gates and OR gates have exactly 2 inputs. Right? Make binary gates. So if I have, for example, an AND gate with 4 inputs, I'm going to transform that into a little binary tree of 2 input AND gates. Similarly, if I have an OR gate with K inputs, I'm going to translate that, I'm going to replace it with a little binary tree of K minus 1 OR gates, each with 2 inputs. Now, this transformation on every gate potentially blows up the number of gates by quite a bit, but this at most doubles the number of wires in the circuit. All right, so if I want to think of the complexity of the circuit as the number of gates plus the number of wires, which you should imagine as the number of vertices and number of edges in a graph, this transformation doubles the number of wires, right? And therefore, it can't make the number of vertices too much bigger. I think you add a new gate, possibly 1 or 2 new gates for every wire in the original circuit. And it's clear that you can perform this substitution quickly. So it takes a little bit of bookkeeping to write down a binary tree of 42 AND gates, given as input an AND gate with 43 inputs. But it's just a matter of bookkeeping. And so the whole transformation can be done in polynomial time. And it also should be clear that the transformation doesn't change what function is computed by the circuit. So if it was satisfiable before, it's still satisfiable after. Okay. Now I'm going to transcribe this new formula, this new circuit. This becomes, for an AND gate, for example, this becomes a clause. It's not a clause in the final form that we want it. But it's going to be a clause that involves at most 3 variables, namely the inputs and the output for every gate. And I'm going to be just ANDing these together. Making sure that, after giving every wire a unique name. Now those upside down V's over there, those are not greater than signs, those are ands. Okay, so again, I'm just going to transcribe the circuit into a formula exactly the way I did last time when I did this circuit to formula reduction. And as we argued last time, the transcription is faithful in the sense that the function that the circuit computes is the same as the function described by the formula. And so one is satisfiable if and only if the other one is. I need to somehow make the clauses into 3CNF form. This requires some bookkeeping, but it's just a matter of, if those of you who've played around with Carnot maps would be able to do this in a few minutes. Those of you who are not will just look in the notes and go, oh, okay, there it is. If I have a clause of the form A equals B and C, I'm going to transform it into 3 clauses, some of which may have 2 literals. And then in the second pass, whenever I see a clause with only 2 literals, I'll add a new variable in and I'll transform it into a pair of clauses with 3. There's going to be one clause in this transcribed circuit that has only 1 literal. That's the output from the circuit. It has to be true. And so in this transformation into 3CNF form, I'll take that lone variable and I'll transform it into this small expression with 4 clauses. And I don't want to walk through the proof that this all preserves satisfiability, but as a sanity check, if you look at this clause that I'm replacing A with, you'll notice that the only way to make this set of 4 clauses ANDed together equal to true is for A to be true. If A is false, then in order to satisfy the first clause, either X is true or Y has to be true. So let's suppose X is true. Well, then in order to satisfy the second clause, A is false and X bar is false, so Y has to be true. But now look at the third clause. Actually, let's look at the fourth clause. A is false, X bar is false, and Y bar is false. The last clause is false. And so because I'm ANDing the clauses together, the whole expression is false. And so I don't have a satisfying assignment. Now, I started this chain of inference by saying, what if A is false? Right? So, in fact, the only solution that works is for A to be true. Once A is true, it doesn't matter what X and Y are going to be. Okay? So, after transcribing the circuit into a formula and then normalizing the formula into something of the correct form, I get this fairly complicated looking expression. Now, when I reduced this example circuit to just a formula without caring about the structure, I got something fairly long, but where every clause clearly corresponds to one of the gates. Now I'm doing something even more complicated because it's got these extra normalization steps inside. And so when I do that, this is the formula that I get, which looks horrible and awful and ugly, but if you walk through the analysis carefully, the total length of this expression, which in this case has something like, 40 variables, is only, the total number of symbols that you need to write down is only at about 20 times the number of wires in the original circuit. And the entire translation from circuit to 3-sat formula can actually be done in linear time. Because it's just made of a bunch of pieces of, well, I need to break up that gate at the end into 2 gates, and okay, that's fine. And then I need to write down a description of every gate, okay, that's fine. And then for every gate, I might need to expand that into 5 or 6 3CNF clauses, which is a nice big constant, but it's just a constant. Okay? And again, I won't do this here, but in order to make this formal, you have to argue, and I would do it by arguing in each step, that the circuit that you started with has a satisfying assignment if and only if this 3CNF formula that you get out of the transformation has a satisfying assignment. Okay? So to sort of draw the picture that summarizes what's going on, I want to build an algorithm that solves circuit SAT. And so I'm going to get a circuit coming in, and I'm going to get either yes or no coming out. Now, someone has magically given me a box that solves 3-sat. Now, I have no idea how this box works, it's magic. So there's a little rainbow on the side. Okay, I just, because every year I have to go to Target and buy, every Sharpie they have. That's red enough. Okay, so there's this magic 3-sat box. I have no idea how it works. There was, maybe there was a unicorn that brought it. Okay, so there's a unicorn hiding inside the box. I just don't know. And so somehow I have to get an answer to my 3-sat problem out of that 3-sat box. So what I do is, using this 3-step process that I just described, I build a new reduction algorithm that outputs some formula, feeds it to this magic 3-sat box, and whatever the 3-sat box says, that's what I return as my output. So this thing here in the middle, then the green, that's my job. I have to write this algorithm that takes in a circuit and spits out a formula. And in order for this to be correct, I need to prove, if I wanted to walk through a formal proof of this, I need to show that the entire algorithm runs in polynomial time, assuming that the magic box for 3-sat runs in polynomial time. And I need to show that the algorithm is correct. And what this boils down to, if you walk through the proof carefully, is proving two claims. One is that if K is satisfiable, meaning if the correct output for the algorithm is yes, then the formula is also satisfiable. Which means the algorithm in fact outputs yes. The other one is the opposite direction. If in fact the algorithm outputs yes, then the correct answer that the algorithm was supposed to spit out is yes. Okay, so one way of thinking about how to split this up is you have to prove that when the algorithm answers yes, it is correct, and you have to prove that when the algorithm answers no, it is correct. An equivalent way of saying this is when the correct answer is yes, the algorithm spits out yes. When the correct answer is no, the algorithm spits out no. But the way that we normally phrase these proofs is basically by arguing that this reduction gives you some sort of equivalence between the affirmative answers for both problems. The transformation takes a circuit and spits out a formula. It's one direction. Only one direction. Nevertheless, the correctness proof has to argue in both directions. When we did the correctness proof here, the way it was structured is the first step of the reduction is correct, and the second step of the reduction is correct, and the third step of the reduction is correct. Okay? And for details of that, you should see the notes. But this is the general outline that we're going to follow, and yes, I do recommend drawing this picture, and yes, if you have a multicolored pen, I recommend drawing the rainbow to remind yourself that that box inside is a thing that you are trying to prove does not exist. This is a myth. There are no unicorns. Okay? But you're trying to prove that by showing that if there were unicorns, then there'd be flying pigs. And we already know there are no flying pigs. Okay. Yeah. So, yes, a polynomial time algorithm for circuit SAT is a flying pig. Okay. All right. Questions? Now, the next examples I'm going to go through are a bit less complicated than this, but I needed to establish 3sat as a baseline so that I could do this. And now later problems I'm going to prove NP-hard I'm going to do by reducing from 3sat. Okay. So, the problems that we've seen so far, you know, they're all the same problem dressed up in fancy clothes. It's you know, no one should really be surprised that circuits and formulas are equivalent to each other. And it's a little bit surprising that this special type of formula is still hard to figure out until you realize, you see the reduction and actually walk through the details, you go, oh, of course. How could it be otherwise? Now that I see the proof, I can see why that would be true. Gates, basically you can make the gates binary and everything else is just bookkeeping. But there are other problems that don't look like Boolean formulas or Boolean functions or Boolean circuits at all. Okay, and so the first one of these that I want to think about is the maximum independent set problem. Okay, so here the input is a graph. And this is not a graph that represents a circuit. The nodes are not gates. The edges are not wires. This is just a graph. Maybe this is a set of people as the vertices, and two people are connected if they like each other as the edges. Okay. And then what I want as output is the size of the largest subset of vertices with no edges. Okay, so if I have a graph, for example, that looks like this, these three vertices are independent. If this is the graph of people connected by edges if they like each other, this is a set of people who can't stand each other. No two people, nobody in this group of people like each other at all. Okay? And I want to find the largest such set. Okay? Now, in particular, I want to find the size of the largest such set rather than finding the set itself, because this problem has the same property that you played with in the lab on Friday. Once you have if you had an algorithm that would tell you how big the largest independent set is, you could use that black box to derive a fast algorithm to actually compute the largest independent set. Okay? I don't want to walk through the details, but this is a sort of general rule for the problems that we're going to think about. It's enough to look for the number of nodes, and if you could show that that problem is hard, it would imply that the construction problem is hard and vice versa. So this is very much like in the dynamic programming world. Instead of actually asking for the longest increasing subsequence, it suffices really to just find the length of the longest increasing subsequence. And then with some small modifications, if you need to, you could find the sequence itself. The same is true here. We ultimately just look at things that intuitively you might want a construction problem, but in fact, you're just finding the size or even just confirming that the size is bigger than some number. And different versions of the problem will have reductions between them that show they're equivalent. Okay? It also helps if I can spell. Okay, independent, not independent. Okay? So I want to prove that this problem is NP-hard. And so I go to my list of NP-hard problems, and I ask, what does this problem most look like? And I say, I have no idea. This is the first real reduction I'm being asked to think of. What do I pick? I just don't know. The answer is 3-sat. And this is a general rule. If you look at the problem and go, how do I 3-sat? Okay? Later on, you'll see another general rule that if all else is equal and you see a 3 in the problem statement, 3-sat. It sounds like a joke, but it really actually works. Okay? So I'm going to try to prove that this is hard. I want to prove that this is NP-hard by a reduction from 3-sat. Okay? So what does a reduction from 3-sat look like? It means I want to assume that there's a flying pig. No, we don't want to assume there's a flying pig, because flying pigs are something else. I want to assume there's a dog who speaks Chinese, namely an algorithm that can find the largest independent set in a graph. And based on that assumption that there's a dog who speaks Chinese, I want to prove that there is a unicorn, namely a polynomial time algorithm for 3-sat. Okay? So let's describe a polynomial time algorithm for 3-sat. So given an arbitrary 3CNF formula, 3 literals per clause, conjunctive normal form, call that phi, I need to produce a graph whose independent set is, for example, larger than some value if the formula is satisfiable and smaller than some value if it is not. Right? And then if I magically had a way to decide how big the largest independent set is, I could use that to discover whether this formula is satisfiable. Okay. Now, here's how I'm going to do this. Okay. First of all, I'm going to build a graph G as follows. First, for every clause, I'm going to have 3 vertices connected in a triangle. And I'm going to label those vertices with the literals inside the clause. Now, the literal A might appear in more than one clause. That's okay. Every instance of that literal will create a new vertex in X, in my graph G. Okay? So if I started out with a formula that has a total of n literals in it, I'm going to end up with a graph that has a total of n vertices in it, grouped in n over 3 little triangles, 1 for each clause. Okay? So in fact, these are all of the vertices, but it's not all of the edges. Okay? So now I'm going to add edges between, let's see, any literal and its negation. So if somewhere in one clause I see an A and somewhere in another clause I see an A bar, I'm going to add a literal. I'm going to add an edge between them. Okay, and this ends the reduction. This is the complete description of how I transform an arbitrary 3CNF formula into a graph. Right? So to show you an example. Here's what the example looks like. And in case you might not be able to see it, here is the formula that I started with. And there is the graph it turned into. So you can see, for example, again, let me try to focus. OK, good. So the first clause says A or B or C, and you see that first clause as a triangle at the top of the graph. Here's A or B or C. Here, the second clause is B or C bar or D bar. You can see that clause over here on the right as a triangle. A bar or C bar or D is here. A or B bar, D bar is here. And then I added an edge between this node and that one because this is a B and this is a B bar, or vice versa. Here's an A bar. Here's a C bar. Okay? Everybody, now, it's at this point, the proper response is, what in the world are you doing? This just looks like I'm farting around and I'm just playing with Tinker Toys, putting things together. What does this have to do with anything? Well, the punchline is that if that formula had k clauses, then I end up with this graph that has 3k vertices. And I claim that this graph has an independent set of size k if and only if the original formula is satisfiable. Okay, so the independent set structure of that graph exactly encodes the satisfiability of the original formula. Okay, so I'm going to walk through this one step at a time because at some point you actually need to see the proof instead of just having me tell you that the proof exists. Okay, so the claim is G has an independent set of k vertices, again, where k is the number of clauses in the formula, if and only if the original formula is satisfiable. Okay? Now, whenever I want to prove a statement of the form A if and only if B, how do I do it? There are two things. There are two arrows up there. Each one needs its own proof. Okay? If I wrote this as IFF, the intuition is that I need one proof for each arrow, or I need one proof for each F. Okay, so step one, I'm going to assume that G is satisfiable. Or sorry, I'm going to assume that phi is satisfiable. There's no particular reason that I need to do one before the other. These are going to be two completely separate proofs. Okay? So choose a satisfying assignment. Okay, so I don't know, maybe I say A is true and B is false and C is true and D is false. Whatever, you know, I don't know what it's going to be. I know there is a satisfying assignment because that's what satisfiable means, but I don't necessarily know what it is, so I'm going to choose one arbitrarily. Okay? Now, because it's a satisfying assignment, each clause has a true literal. Maybe it has two, maybe it has three, but it has at least one. So I'm going to pick, for each clause, one of the literals that's true. Okay? Don't care which one. Now, I've chosen a subset of the literals in my clause, in my formula. Now remember, these literals correspond exactly to the vertices in my graph. So I want to claim that this subset of vertices is independent. Well, I don't have any, only one per clause. So there are no edges from inside those triangles that connect two of the selected nodes. And so the only other place that you could have an edge, if it's between a literal and its negation in two different clauses. So no long edges because every selected literal is true. And so if I look at this example, right, I've chosen a satisfying assignment that has A is true, C is true, D is false, and whatever, I don't care about B. Maybe B was true. I chose one of the literals from each clause to be true. So for example, in this clause down at the bottom, A bar or C or D, which is on the upper left side of the screen, I chose the literal C, which means I chose this vertex. Right, so I've chosen a subset of the vertices, and now I need to convince you that this subset of K vertices is independent. So that means there are no edges between two of the marked nodes. Well, there aren't any triangle edges between two of the marked nodes because each of the marked nodes is in a different triangle. And there aren't any long edges between two marked nodes because I only mark a node if its literal value is true. And so if I had a long edge between, say, A and A bar, I can't mark both A and A bar. At least one of those edges, one of those vertices isn't there. Okay? So this is, in fact, an independent set of size K. All right? So this is the first half of the proof. So G has an independent set of size K. Now there's a second proof which is similarly definition chasing. Suppose G has an independent set of size K. Then it must have, that independent set must have exactly one selected node from each triangle. I can't have more than one node in a triangle because then they wouldn't be independent. I can't have less than one node in the triangle because then there wouldn't be enough marked nodes. Yeah?
But you are getting the largest subset.
Yes, and remember, my black box is going to tell me the size of the largest subset. If that number is K or bigger, then there's an independent set of size K, and I know the formula is satisfiable. If that number is less than K, then there's no independent set of size K, and I know the formula is not satisfiable. So if there's an independent set of size K, it has one node in every triangle, and those nodes must have consistent truth values. So I can derive an assignment of values to the variables that satisfies the original formula. So there's a second proof, which is actually the one that's described in detail in the notes, that says if I start with G has an independent set of size K, I can walk backwards and conclude that the formula is satisfiable. Okay. When you do NP-hardness proofs, there are three things for you to write down. 1, describe the algorithm. 2, prove one way. 3, prove the other way. The fact that the algorithm runs in polynomial time, you also have to write down. But it will always be true. It's really actually quite difficult to come up with reductions that don't run in polynomial time. Right? The things that will occur to you naturally will run in polynomial time. Unless it's like try all possible something. Right? Don't do that. You're trying to solve the problem. You're trying to do a reduction. So you also have to write down algorithm runs in polynomial time. But that's one point. writing down the algorithm is 3, and each half of the proof is 3. Okay, so this is 3 points, 3 points, 3 points, 1 point. And the way you get that point is writing down the reduction runs in polynomial time, period. And that being true. Okay. All right. So I'm going to ask you to do the next one, or maximum independent set. Okay, so this is the maximum clique problem. This is in some sense the opposite of the previous problem. Again, I'm given a graph, and again I want to choose the largest subset of vertices, but in this case I want the largest subset where every pair is connected. Now, the maximum number of vertices that are all pairwise, all pairs are connected. So in this graph that I drew earlier, this would be, for example, these 3 vertices. That's not the only possible choice, but for this particular graph, the output from the Max Clique algorithm would be 3, because there's no clique of size 4, where every pair is directly connected. Okay? I would like you to prove to me that this problem is NP-hard. And to do this, I need to describe a reduction from one of these 4 things, since these are the things we already know are NP-hard. Now, which one of these problems looks most like maximum clique? Maximum independent set, because both problems are asking you to find the largest subset of the vertices that has some property. That's good enough for me, okay? So I want to describe a reduction from max independent set, okay? So how do we start the reduction from maximum independent set? What do we start with? Okay, assume polytime algorithm for Max Clique. Good? What do I want to derive? What do I want to derive from that algorithm? Well, what does it, let me back up a second. What does it mean to reduce maximum clique to maximum independent set? Right. So I'm going to build a polynomial time algorithm for maximum independent set. Okay, so again, I have my Max Clique algorithm. It spits out some number k, and I want to build from that an algorithm that has maximum independent set. Some graph G will come in, and somehow I have to build a thing that goes in the middle that connects this graph to this box. And it will spit out the size that what actually comes out here is the size of the largest independent set in G. Okay. Now, what's going to go into the clique box? What is the input to the clique problem? A graph. What should we call that graph? G prime. Good. It's not G. It's not the same graph. Because there are graphs, if I take a graph where every node is connected to every other node, the maximum independent set size is 1. The maximum clique size is however many vertices there are. Right? So I need to do something non-trivial here in the middle. So what do I do in the middle before I, feed the, I need to feed something called G prime to the magic box that the clique fairy threw in my lap. At least 3 of you know the answer. 1, 2, 3.
When you just need to replace if it has an edge.
Right, so here is how I'm going to build G prime. So remember, G is a set of vertices and a set of edges. So G prime uses the same set of vertices and the complement of the set of edges. So if I have, for example, an edge between 2 vertices in G, those corresponding vertices will not have an edge between them in G prime. But if there's no edge in G, then there will be edges in G prime. Okay? Now, 2 vertices are then, more or less by definition, 2 vertices are independent in G if and only if they're connected in G prime. And moreover, a set of K vertices is independent in G if and only if that same set of K vertices is connected in all possible ways in G prime. Every independent set in G is a clique in G prime and vice versa. Right? So there's a one-to-one correspondence between independent sets here and cliques there. Okay, so what my reduction will do is it will take, for example, maybe the graph is given to me as an adjacency matrix because I don't really care what the exact form is. Suppose I'm given an adjacency matrix for G. I'll compute the adjacency matrix for G prime by swapping every 0 for a 1 and vice versa. Then I'll feed that new adjacency matrix for G prime into the magic box for clique, and it will tell me G prime has a clique of size k, but no clique of size k plus 1. Because of this correspondence, that tells me that G has a clique of size k, but no clique of size k plus 1. This reduction runs in polynomial time. Okay, I had 2 for loops. For I equals 1 to n, for j equals 1 to n. Replace a bit with its negation. That's polynomial time. Okay? So again, the reduction, one way. The proof, if and only if. But in this case, the if and only if proof actually just derived directly from the if and only if definition of G prime. There's an edge between 2 nodes in G prime if and only if there's no edge between those vertices in G. Okay. Good. So let's do one more. Okay, so now my goal is given a graph, not to find the largest set of vertices with some property, but to find the smallest set of vertices with some property. Okay, so and what that property is that I want every edge to have at least one of its endpoints inside this subset of vertices. So if I look at this graph again and the collection of vertices that I've colored in, every edge in the graph has either one or two pink endpoints. Could be one, could be two, I don't care, right? So the diagonal edges are covered twice, the horizontal and vertical edges are each covered once. So for this particular graph, the correct answer to the minimum vertex cover is 3. Okay? Now, this is a little bit different from the problems we've seen so far, because now instead of looking for a large subset of vertices, I'm looking for a small subset of vertices. But nevertheless, I claim that you guys can figure this out. So what problem does this kind most resemble? Really thinking about it too hard. Yeah. Yeah, it kind of looks like either max independent set or maximum clique. And without thinking about it too hard, how do you think you're going to get from transforming the output of some magic box for this min problem and getting the correct output to some max problem? I want to establish some kind of trade-off. The larger the independent set I get, the smaller the vertex cover I get, and vice versa. So if I want to show that somehow maximizing one quantity tells me immediately that I'm minimizing the other. Okay. So yeah, you're right. I'm going to reduce from maximum independent set. Okay, so here's my black box that gives me my minimum vertex cover. There's a graph that goes in, there's a number that comes out. And I want to build a box that solves max independent set. And there's a graph that goes in, and there's a number that comes out. Okay. I'll give you a hint. Don't actually change the input at all. It's the same graph. Okay? So I claim that I just need to figure out how to transform the output. Now this is a little different from the reductions we've seen before. But it's okay. I mean, we're trying to just build a polynomial time algorithm. We can do all sorts of things in polynomial time algorithms. We could call that middle inside black box, I don't know, n squared times with n squared different subgraphs. But in this case, it's actually pretty simple what to do. So look at the example up there of a vertex cover. Do you notice anything about the white vertices? They're independent. Because if they weren't, if there were an edge between two of the white vertices, that would mean the pink vertices don't cover that edge. So it wouldn't be a vertex cover. Okay? So in the end, the answer is subtract. Okay? if some subset of V is a vertex cover, in fact, this is an if and only if V minus S is an independent set. Right, so if I have an n-vertex graph and it contains a vertex cover of size 20, it must contain an independent set of size n minus 20. If it contains an independent set of size 20, it must contain a vertex cover of size n minus 20. So by trying to make the number of marked vertices in the vertex cover as small as possible, I am simultaneously trying to make the number of unmarked vertices in the independent set as large as possible. So in the end, the reduction just looks like this. Okay. On Thursday, we will see some somewhat more complicated looking reductions. This is graph coloring. This is traveling salesman. But I should tell you before we start getting into the more complicated examples, this is approximately the level of difficulty that we will ask on an exam. There'll be one step, you have to glue in one gadget. The whole 3-sat to maximum independent set thing, that's very clever. We wouldn't expect you to do that on an exam. Still, it's useful to see the more complicated examples to build up some intuition. All right, thank you. See you Thursday.